Yeah, hello. First, thanks a lot for letting me talk. I'm happy to be here and talk about towards an internal construction of meaning. So I'll explain the towards, and because I do not come from a formal logic background, so maybe some things that I'm presenting may require some clarification. I just don't. Well, all that makes a lot of meaning to me mathematically, but I'm not sure about the syntactical, logical counterparts, so maybe some of you will know. So at first I just wanted to clarify a few things for myself regarding the foundations of category theory, and notably with regards to this collection of objects I was dissatisfied with, and the notion of a size as well. So I tried to clarify some stuff for myself, and I just ended up with a hierarchy of end categories where each level just internalizes the level below, and so the way I'm going to present it, maybe it won't be clear that this process of thought will not be, because it may look like I was trying to do something from the beginning, but it's just something that arose as a necessity when one wants to always consider an object as an element of another object. Okay, so why am I saying that? I'm going to cite some people, not only to hide behind authority, but also because I think that there is some view of mathematical logic that is older than Hilbert, and that may have been forgotten during modern since Hilbert. So this view I'd like to present is a Leibniz one. So his idea of mathematical proof and truth was quite different than the one we have now, but not that different actually. So he says that necessary truths are identical, some explicitly, these are the first truth or axioms, and others virtually or implicitly, and these are the demonstrable theorems. So, and then most importantly, he says that to demonstrate the latter is to reduce them to identical truth by analyzing their terms, that is, by defining them. And so every demonstration consists in substituting the definition for the defined, that is, in replacing a complex term by a group of simpler terms that is equivalent to it. So this is precisely what I'm going to do today, but okay, so that's the essential foundation of deduction is the principle of the substitution of equivalence. This is a supreme and unique principle of logic and not the principle of syllogism, for the latter is a theorem that is itself proved by means of the former principle. Okay, so this is based on an analysis of Couturat from Leibniz logic. So I hope this will clarify what I'm trying to do after that. Okay, and so because sometimes there is a confusion, Gödel just ended up Leibniz project, but I think that this is not true, and Gödel himself was very aware about that. So he says, he keeps insisting on the fact that primitive concepts need further elucidation. So he says that many symptoms show only too clearly, however, that the primitive concepts need further elucidation. So it seems reasonable to suspect that this incomplete understanding of the foundations which is responsible for the fact that mathematical logic has up to now remained so far behind the high expectations of Peano and others who, in accordance with Leibniz's claim, had hoped that it would facilitate theoretical mathematics to the same extent as the decimal system of numbers has facilitated numerical computations. And he says after that there is no hope to give up, there is no need to give up hope, because Leibniz did not, in his writing about the Characteristica Universalis, speak about an utopian project. So I don't know if you know what is Leibniz Characteristica Universalis, but it was Leibniz's project of formalization of language. And so he wanted to construct a process that reduces symbols to truth, and only by substitution of definitions. So, okay? And then he gives an important example, that is that the very existence of the concept of class constitutes already such an axiom. Well, it's something. Since one defined class and in to be the concept satisfying the axioms, then one would be unable to prove their existence. And so I think this sentence illustrates maybe my own confusion with regards to like the distinction between a deductive system and a model, because we always end up having undefined terms that are maybe not as clear as one could expect. Okay. So we can just wonder whether this distinction between syntax and semantics is necessary. This is quite a recent distinction that did not existed before. So yeah, so I'm just here recalling what Gödel just said. So yeah, so there is two different kind of axioms, and because some of them are just only definitory and others are like assumptions. And so axioms serve often as a definition because we can just define a concept as a concept that satisfies the axioms. And so yeah, there is still an ambiguity that remains because of those undefined terms, because when you consider a model, if you take a model if in a category, then what is a category if we don't know what a set is, and if all of that is axiomatic and not actually defined. So the thesis I'm trying to defend here is that the distinction between syntax and semantic is actually responsible of some foundational issues, and notably, but not only, because it yields redundancies and complications. And so I think that this is a consequence of the lack of definitions of certain concepts. Okay, so to address this issue, the idea is to organize the objects into a hierarchy, and so we can define like a set as that of like objects and an equality between each pair of elements. But then we're just wondering, but what is a set? And then we can actually define a set as an element of the two category of categories, and inductively like that construct any objects without relying on any undefined term. And so to do so, I also propose to internalize the notion of a typing judgment, and by expressing them as truth values, which just corresponds to the -1 level of the hierarchy. And so by using definitions, the idea is to address the junction between syntax and semantics by definitions and substitution, so that at first it's just a syntactical expression that does not have a meaning, but once all the pieces of the puzzle have been defined, the whole syntax makes like a semantics emerge from all this. Okay. Yeah, so let me first maybe excuse in advance, because all of those things are highly non-linear, and given that everything must be defined piece by piece, and the meaning actually does not emerge before that everything is defined, but time being linear, I cannot, so maybe I should also make like call for your intuition and for as first. Okay, so yeah, to formalize the notion of a type constructor and which is internal equivalent or counterpart of a typing judgment that I'm using to internalize the definition process. So I just encode those type constructors as a map. It will be defined after from a set of symbols to the poset of truth values. So L here is the poset of symbols that we use to write. So I wrote po under brackets because here I'm not sure what is the best way to do so. So either by a set or a poset, because it will after that encode the concept of substitution, and maybe we want to keep a track of which element have been defined and which is the shortcut, like the denotation and the meaning. So I'm just okay, and it's constructed dynamically in that at any time we can just choose to define something by using the symbol like that, the usual one. And each time something like that is written, it will introduce a literal equality between the symbol X and Y. Okay, here maybe I have not well chosen my notation because during all of the talk, okay, so here this notation just means that X and Y are related as elements of L by a truth value. So this means that here is L is a set. This means that those are equal, okay? And B is the poset of truth values, and I will define it later. So to understand what does that mean? So this map will map a symbol to a truth value, and this truth value actually gives conditions for a symbol to be defined as an actual element of X. So we can either work formally by deriving logical consequences of this expression that will be given a meaning if it is defined, or provide a proof of this expression. And if there is some small x that is equipped with a proof of the truth value, then we will say that it is an element of X. And a proof of the truth value actually corresponds to a definition. But it will become clearer in a minute, I hope so. Yeah, okay. So the fundamental constructors that I defined are those of n categories. So, okay. So in one sense, it is an analytic principle. So it's consisting in decomposing the parts of which X is made. So an n category here will consist in the following data. So some way to construct some objects and an n functor that will give the n-1 category of morphisms between objects of this n category. Okay, and so the reverse direction can be seen as a synthesis, like so, because on the one hand you have an element of we have that n categories are constructed by using the level below, which is an analytic thing, and on the other hand any n category, yeah, if you have something like that, you can see the object, you can see, yeah, you can just gather the information and treat the object as just internally into a higher level. Okay. So this does not have a meaning for now, of course, because this does not. And yeah, so everything is nested here, so I hope it's understandable. Okay, so this is a definition of an n-functor, and it consists of a mapping that to any element of y associates an element of z, and this is a functorial part of the definition, which means that to construct an n-functor between n categories, you need to associate. So this is notation I won't have time to explain now, but this means that for all x and y in y, then you have to provide an n-1 functor from the n-1 category of morphisms in y from x to y to this thing. Okay, so okay. So for this definition to have a meaning, we have actually to prove that that we have an n category of n-1 categories. And this is done inductively on n, with a little micmac at the first, the -1 level of truth values, which I will explain in a minute. So here I've just substituted cat n-1. I've substituted x to cat n-1 in this expression, and to obtain this thing, okay. Okay, and yeah, let me maybe. So the idea is that so here this is the n-1 category constructor that is encoded like that, and this is a proof of this truth value, actually. Not now, of course, because this has to be given a meaning. That is, it has to be associated with a truth value, so that this is something more than syntactical, and so that it becomes semantical, actually. Okay. There is a question, because okay. Yeah, so I wanted to talk about the definition process, because this is actually some things that I'd like to have opinion on. Yeah, so it's encoded, like I said earlier, by this symbol, and yeah, and the way I see it is that it just updates the poset of symbol, and by introducing an equality. So if it was a computer, it's just like it was the L was like the memory, and this symbol just assigns this thing to this address or something like that. Okay, and so this expression just can be seen, should be seen like as a proof of the literal equality, which I write like that because of, maybe I should. Okay, if you take the definition for n equals 0, you obtain, and I will go back to it in a minute, but yeah. You obtain actually the formalization of Bishop's notion of a set. That is that to construct a set, you have to explicitly give the equality between each pair of elements. Yeah. Okay. Yeah. So now we can actually give a definition of those type constructors that. Sorry. I was talking about just earlier, thanks to the definition of morphisms from the slide below. So yeah, so for each, so having a map from my poset of symbols to my poset of truth values consists of assigning a truth value to each symbol, and most importantly, because this condition actually encodes the concept of substitution. Whenever I have an equality or a map in the poset L between two symbols, then it should yield a logical implication between the image of this constructor, which allows to derive the fact that if I define x as being y, and if maybe I should have written it in the other direction so that it's more meaningful, but it doesn't matter because I want it to be symmetric maybe, and so you obtain that y is an element of x as soon as x is. Okay, hope it makes sense. Yeah, so if we look at the definitions obtained for truth values, yeah, okay, I've cited just the meaning of logical rules is to be found in the rules themselves, which I have taken from a paper from Jean-Yves Girard, the meaning of logical rules, that is, that has like funny phrasings of meta-linguistic considerations. So he says that the rules of logic has been given to us by Tarski, which in turn got them from Mr. Meta Tarski, and so he argues in favor of logical internal reasoning in logic, So if we look at the definition obtained for truth values, we obtain that a truth value, is the following, and it is here that. So the heart of the internalization of meaning lies in the identification of this B with with -1 level of the hierarchy. Because what I forgot to say before is that the B here is indeed the truth values, but it is actually also it gathers the symbols to which we want the statement to be evaluated in the end of the process of demonstration. Okay, and so there is a bit of like hard coding to be done, because given that anything that is written is actually expressed as a truth value, we have at the beginning to express those as like to fix some notation and then check that the poset obtained fits into the hierarchy, because those definitions are very rigid structurally, and it imposes a lot of stuff, so we cannot do anything that we want. But here, the implication that is encoded, if we want to have the, so here it is Boolean truth values, so there is false and true, and we state at the beginning that false implies true, and true does not imply false. Okay, and after that I wanted to write it, but okay. Okay, so if we look a little at this definition, so cat -1 will actually correspond to true by definition, so we can just substitute it, and yes, the arrow is just also a shortcut definition for this thing, and because of this hard coding, this evaluates to true. And this also evaluates to true. I'll come to it in a minute. And after that, yeah, so the conjunction is also fixed at the beginning, and then we check that it satisfies the universal property of a Cartesian product, and so we obtain actually this thing. So this is something that is quite important, because this definition encodes the fact that a truth value corresponds to its proof. So yeah, okay, so what is truth here? So I've only written it for true, but the same holds for false. And by this definition, or we actually obtain a semantic equivalence, which means that we have an equivalence within the poset of truth values, that the true have an element, proof, is true, and this expression cannot be expressed in a type theory, namely because the typing judgments are judgments, and true is not a judgment usually, and cannot be defined internally to a type theory. So yeah, so this is a key feature of this framework that aims to gather syntax and semantics. Okay, and so the proof of true is to be seen as the smallest semantic unit, because any definition consists in providing a proof of the type constructor that I talked about just a few minutes ago, and this proof is the definition, and it contains the information that allows for the definition of the object. Okay, yeah, and so any mathematical truth is just constructed by using this the definitions, and hence the proof, those semantic units. Okay. Yeah. Okay. So I just wanted to go back on Bishop's set, because I guess that the definition that I mentioned is not very clear. So yeah. So he says that a set is not an entity which has an ideal existence. A set exists only when it has been defined. And to define a set, we prescribe, at least implicitly, that we, the constructing intelligence, must do in order to construct an element of the set, and what we must do to show that two elements of the set are equal. And a similar remark applies to the definition of a function. In order to define a function from a set A to a set B, we prescribe a finite routine which leads from an element of A to an element of B, and shows that equal elements of A give rise to equal elements of B. So looking at the definition, this is exactly the definition that I'd obtained for a set, and the category of set that results from that definition satisfies all of the axioms of Lower's elementary theory of the category of sets. So we obtain a set theory that is just exactly a formalization of Bishop's notion of a set and a function. And to go further, just okay, we can actually slightly change this thing to make it compatible with higher levels, because this is okay. So in this framework, to show that two elements of a set are equal just consists in constructing a truth value that expresses the equality between each pair of elements. And to show that equal elements of A gives rise to equal elements of B corresponds to constructing a logical implication from the truth value that expresses the equality between each pair of objects of A to the truth value that expresses the equality between the image pair by the function of objects of B. Okay, and so yeah. So here, an N category is not an entity which has an ideal existence. It exists only when it has been defined. And to define an n category, so we prescribe explicitly, that is the idea of all this. What we must do, but maybe ideally the computer, to construct an object of the n category, and what we must do to construct the n-1 category of morphisms between each pair of objects in a natural way. And the natural way gives not only the composition in n categories, but also the coherences. Okay, and a similar remark applies to the definition of an n functor. So in order to define an n functor from an n category A to an n category B, we prescribe a finite routine which leads from an object of A to an object of B, and construct an n-1 functor from the n-1 category of morphisms between each pair of objects of A to the n-1 category of morphisms between the image pair of objects of B in a natural way. And the natural way will encode the functoriality of the n functor. Okay. I tried a toy example, but because I think it illustrates the distinction with formal frameworks well, because to construct the empty set in type theory, you just say that there is no way to construct an element of the empty set, and here you just state that being an element of the empty set is wrong by definition. Okay. Okay, and formally this would look like that. So the predicate of objects sends any symbol to the truth value false. Okay, and on the morphism, I don't remember if I no. Okay. Okay. So on the morphism, you obtain that that this line evaluates to true because of the definition of the logical implication, and so this is the map that gives the equality, but here we do not have elements, so actually we can just set anything that we want, and it will give the correct, and it will evaluate to true this thing, because we have ex falso quod libet here, so, and given that this always evaluates to false, anything that comes here will make the whole thing evaluate to true. Okay, and same for here. Yeah, I haven't talking about the opposite, but it's something that is also defined, and it swaps the variables, and so, okay, here, yeah. Okay, so here, because true is defined as provable, and because the negation of true, the negation of true is false, the statements "I am not provable" and "this sentence is false" both correspond to a fixed point for the negation. But the diagonal argument cannot be used here because it is contravariant, and Gödel's theorem actually is a syntactical result, and he was perfectly aware about that. This is just as it was. Because he still had hope with this project of Leibniz, so I think that this could be taken seriously, actually. So this is a hope, and about okay, and in Boolean logic, which is the one that I use to construct the hierarchy of n categories, being an element of type B is logically equivalent to being either false or true. So we just obtain that. Yeah, I haven't explained that maybe. Okay, but I'm going to go faster because, okay, we can actually have a framework like that where a truth value is equivalent to its own negation, but it is not what we want here because, because when the truth values are fixed to true or false, we obtain the notion of a set, which is quite cool. Okay. Okay, so this logical statements actually evaluates to false. Okay, so another hope is that classical set theoretic results do not a priori hold into this framework, because it's not the same framework. And so for instance, and there is actually a lot of things that change. So I don't know if Cantor-Bechstein theorems hold in this framework, because I've just identified two proofs that do not. And the reason for that is that one of the proofs, for instance, I don't remember the other one, but it involves the construction of a subset, which is a limit of subsets. And in this framework, there is a modified equality that is much more rigid than in the one in set theory. And so, yeah, it tells identification on the elements of the limits. So the subset obtained is actually not a subset anymore, it's the quotient of a subset. And yeah, and quotients in general do behave differently, because we don't have, there is a significant loss of information when we do quotients in this framework, and we cannot access the elements of the equivalent classes, and this causes a lot of modifications in the resulting set theory. So yeah, and also something I wanted to say is that the objects of an n category are like not discernible as standalone entities when n is strictly over 0. So it does not make sense to talk about equality of objects, and so it does not make sense either to forget about higher cells or something like that in this higher categorical framework. So yeah, and and I think this is a good point, actually. Okay, so the hope is that there is no threat against the existence of a functor like that, which seems quite natural, which is not the case actually in classical set theories, and yeah, and more generally, yeah. So the hope is to allow for sets to form a whole and not being graded into universes. Okay, and there is still a way to address the notion of size internally, and by grading. So the notion of size is graded, and small objects will be the objects that come from the levels below by inclusion. So for instance, a small category is a category that is equipped, whose object is equipped with an additional equality relations on the objects. Okay, and I'll stop there.
Questions?
So what happens for infinite category? Not truncated?
Infinity categories can be constructed by using, so the definition of an infinity category that I obtain is corresponds to the data of an n category for each n, with each of the levels related with them other by using those interdimensional connections. And the interest of that definition is that we can construct an infinity plus one category of infinity categories and infinity functors. And the shift is syntactical, but it allows for having an infinity plus one category of infinity categories. And yeah, and this is related to this ongoing project I have to provide the semantics for directed homotopy type theory.
More questions?
Thank you. You had this slide where you said that truth cannot be expressed in the type theory.
Yeah.
I wonder whether you have anything to say about Brouwer's intuitionism, where, of course, we can also not directly express truth by the undefinability, but we have something kind of like it, right? We have this this creative subject, which has introspective powers, and if an assertion is known to to that creative subject, then then there will be a time n such that it's known at that time. Does this somehow fit into your framework?
I don't know. I need to look at this. I haven't thought about it.
More questions? So I would have a question. Composition. So you said that composition arises because the Hom objects are defined naturally,
Yeah.
in a sense.
Yeah.
Can you elaborate that?
Yeah. I can rate it. If you
Um,
want. It is like the analogous of path induction.
Path induction.
Path.
A path induction.
Path induction.
Ah.
Yeah. Okay. Where can I find? Do you know where can I find a?
The chalk.
Ah. Thank you. Okay. So. Yeah. So suppose you have an n category. So in particular, you have this, yeah. Okay, so by definition of this n functor, it consists in associating for each objects of x an n-1 category. And the naturality conditions is expresses as follows.
So you presuppose the Hom functor when you define the Hom sets.
The Hom set of what?
Or the Hom objects. Sorry.
Yeah, if X is an n category, yeah, it comes with an n functor like that.
Mm-hmm.
And
Okay.
so,
I think it's
yeah, in fact, the composition is not like binary as in like classical definitions, but it takes actually three. Okay. Yeah, you know, it's cubical, like.
the naturality in both variables simultaneously.
Okay, so you have, yeah. And the composite is post-composition and pre-composition. And after that, yeah, the naturality just have schemes like that.
Okay.
I would have to write bigger diagrams if you want.
I get the idea, I think. Are there any more questions? Otherwise, let's thank the speaker again.